So by now it's been nearly 100 years since people first stitched together the core mathematical ideas of quantum theory. But in all of that time, we've never been able to reach anything like a consensus over whether that mathematical formalism can paint us anything like a clear and observer-independent picture of reality. And so it wouldn't be unreasonable if we just concluded that the task was too hard, that humans trying to interpret quantum theory is a bit like a dog trying to figure out how ChatGPT works. But despite that, I want to argue that there are good reasons to be more optimistic. And in particular, if you look at the literature on quantum foundations over the past 10 years or so, then I think that there are at least two key developments, two kind of reasons for hope that really stand out as suggesting that there might be considerable progress yet to be made on the interpretation of quantum theory. And the first one of these reasons for hope is the articulation of and the no-go theorems for what people call the absoluteness of observed events. So to understand what absoluteness means, think about some kind of experimental situation in which you would ordinarily or naively be inclined to say that there are n observations that take place. At a minimum, absoluteness is going to commit you to saying that you can completely describe all of those observations just by listing n variables, each of which is going to take a unique value on every run of the experiment that just completely characterizes the corresponding observation. And this is a deeply natural assumption, right? It essentially just encodes the idea that whenever an experiment is performed, there's always a definite and unique fact of the matter about what everybody sees. And yet, despite how self-evident it may appear, we do have these no-go theorems. Now, for me, this is just background. So I'm not going to attempt to describe these no-go theorems in any great detail. But what I can do is just give you a brief sense of one of the key take-home messages that I think you get from studying a number of these results. And that's that if we really want to do justice, if we really want to believe in and do justice to our two best theories of physics, to unitary quantum theory and to relativity theory, then these no-go theorems push us fairly hard towards giving up on absoluteness. Which isn't to say that there aren't any loopholes that we might think about trying to exploit. There are, but I am claiming that the loopholes don't appear particularly attractive, and that it's more likely that if we really are going to hang on to the core principles of these two theories, then the way that we're going to do it is by giving up on absoluteness. But more than that, even if we're not committed to these two theories, even if we're happy to say something like, maybe unitarity isn't universal or something like this, then we still have pretty good reason to believe in non-absoluteness. There is a recent paper by me and Vilasini Venkatesh and John Barrett where we showed that any reasonable physical theory that satisfies three properties, which we called Bell non-locality, information preservation, and local dynamics, also inevitably leads to one of these no-go theorems. And so that strengthens the case for rejecting absoluteness. So from now on, I want to assume that the way that we're going to respond to these no-go theorems is by rejecting absoluteness. But that's easier said than done, right? Because it's easy to state positively what absoluteness means. It's a lot harder to articulate a satisfactory sense in which the assumption can fail. But that's a good thing, because that gives us a good place to focus our attention. And it might be that in endeavoring to articulate a more satisfactory conception of event relativity, we ultimately get led to a more satisfactory interpretation of the whole quantum formalism. And that's really going to be the theme today. So it seems the most likely thing, if events can fail to be absolute, that it's because in some sense they're kind of relative, so that we get pushed towards saying some weird sounding things like a bomb can explode relative to X, while the same bomb doesn't explode relative to Y. And there are attempts to make sense of this rather strange-sounding idea. So on the Everettian approach to quantum theory, you say that X and Y are different branches of the universe, or different worlds. Now, clearly the appeal of this idea is going to depend on what you think is the appeal of the Everett interpretation more generally. But one particular problem that you might have with this conception of event relativity is that many, if not most, of these Everettian branches, these worlds, do not follow the Born rule statistics even approximately. And that, at least prima facie, would appear to undermine our usual assumption that it's precisely the Born rule frequencies that serve to confirm quantum theory, And conversely, that if we started observing different frequencies, then we would be justified in rejecting the theory. Another approach is to say that X and Y are different consistent sets of histories, which certainly has some merit to it. But one issue with this approach is that in some sense there are arguably just too many of these consistent sets of histories to choose from. My problem here isn't a sort of Occam's razor point. It's rather this point that Faye Dowker and Adrian Kent made at great length in one of their papers, which is that in some sense the sheer multiplicity of the consistent sets that we can choose from can lead to some problems when it comes to trying to predict and explain the approximately classical character of most of our experiences. But hopefully I should have to say more about that issue, and I'll definitely have much more to say about consistent histories later on. For now, let me mention a third existing conception of event relativity that we get from various relational approaches in which X and Y are some sort of observer. Now, I don't think that these approaches suffer from those same problems that afflict Everett and consistent histories that I just mentioned a second ago. But I do think it's fair to say that they suffer from an even more fundamental problem, which is that essentially, at least in their current incarnation, these approaches are just a bit vague. You can put the point historically if you want. I probably won't get much pushback if I say that at least since the time of Galileo and Newton, probably since even before then, physics has really made the great progress that it has made by reaching a higher level of conceptual clarity than is possible when you're using ordinary natural languages. And it's achieved that higher level of clarity by translating ideas into precise mathematics where it's possible to do so. But the problem with these relational approaches is that often the most important and the most counterintuitive claims, and the most interesting ones, are not translated into any precise mathematics, which can make it difficult to understand exactly what they mean. So for example, the sort of claim that's quite common if you look at the literature on Ravelli's approach to quantum mechanics, Ravelli's relational quantum mechanics, you get claims like events obtain relative to the system that observes as a result of an interaction with the observed system. Now, as will become clear later on, I think that there's a lot of merit in this. I think that there are some deep insights there. I think it's really onto something. But without a precise mathematical theory in which to anchor our intuitions about what these various words mean, it's just difficult to understand precisely what's being claimed. And so although I think this part of the literature is a great place to look for interesting ideas and inspirations, it's fair to say we've not yet been given anything with the level of mathematical rigor and conceptual clarity that we typically do expect, and I think that we should continue to expect from a theory of physics. Okay. But that's exactly where I think the second key development, the second reason for hope, can come in very useful. And now I'm talking about the discovery of a surprisingly natural and elegant and even useful theory of causal influences in quantum mechanics, so-called quantum causal models. I think that the notion of quantum influences at the heart of these quantum causal models, or at least a fine graining thereof, are going to be just what we need to articulate a better understanding of event relativity. This understanding of event relativity is going to be one that avoids the problems with consistent histories in Everett that I mentioned, and which formalizes some, although importantly not all, of the ideas from the relational approaches, but which also does so in a way that hopefully is much more conceptually clear and mathematically precise. And so it's going to lead us to a precise and observer-independent reformulation, or an interpretation of quantum theory, in which causation plays a very fundamental role, and our ontology is an ontology of relational events, but they are relational events that emerge naturally from that more fundamental underlying causal structure. And making all of this clear and explaining to you this interpretation is really going to be the subject of this talk. And I should mention, by the way, that all of this work on this interpretation is joint work with me and John Barrett, and it's based on a paper that's currently in preparation. Cool. All right, so the first thing to do is to get clear on exactly what we should mean by causation, at least in this context, starting with the classical case. So it is commonly believed that causation has something to do with signaling, and that's right insofar as if I want to send messages to you, then I can only do so if there's a causal influence that can carry the message, and so signaling implies causation. But the converse implication doesn't hold, and that is important to appreciate. You can see this easily with a simple classical example of a C0 function that takes the bits I and j to I and j plus I, a classical C0. If you give Alice access to the target input and Dexter access to the target output of this transformation so that Alice can choose the value of I and Dexter reads out the value of j plus I, then you can ask yourself the question, can Alice signal to Dexter? And you might be tempted to immediately say yes because of the definition of the function, but actually the question is, it depends. It depends on what the agents know. Because if the agents don't know that initial j value, then this is useless. They can't send each other any messages. And so what I think we learn from this is that signaling has something essentially to do with agents and what they know. But we should resist the idea that causation has anything to do with those things. At least in this example, it seems kind of clear that we should say that there's causal influence from Alice's system to Dexter's, because Dexter's system is literally functionally dependent on Alice's, which motivates the following definition of causation in the classical case. There's a causal influence from the variable A to the variable B, if and only if the variable B depends non-trivially on A in the function that fully describes the dynamics. So on this approach, the full function tells you the whole dynamical structure, including exactly how one system depends on the other, but the causal structure only tells you whether or not one system depends on the other. Causation here is a coarse graining of dynamics. Dynamics is the full how of influence, causation is just the whether or not. Good. So if classical influences are functional dependences, then it's natural to think about quantum influences as unitary dependences. And an obvious way to formalize that is to say that if A is an input subsystem and D is an output subsystem to some unitary transformation, then we'll say there's no causal influence from A to D, if and only if, when I trace out all of the outputs except for D, I am left with a channel that essentially just traces out A. Which seems fair enough, but you might sort of worry that maybe there are other inequivalent notions of causation in quantum theory that seem equally reasonable. But at least in the finite dimensional case, and all of this talk is going to be about the finite dimensional case, this really doesn't appear to happen. There are various bits of the literature in which you'll see someone prove that this notion of quantum causation is equivalent to some other notion. There is a recent paper that's come out in Quantum with me and Augustin van Rietvelde and John Barrett, in which we collected together some of these existing notions from the literature, we added in a few of our own, and we proved that no less than 6 different notions of quantum causation are equivalent to each other, even though many of these different notions express really quite contrasting intuitions about what causation should be about. Which is kind of cool. It kind of indicates that we're onto something. It suggests that there is a kind of clear canonical and correct notion of causation in quantum theory. Now, I won't bore you by trying to go through all of these different notions, but it is worth paying attention to that algebraic formulation of no causal influence at the end over there. So what the condition in white is saying is that if we take an arbitrary operator that acts only on A, and we transform it through into the Hilbert space for C tensor D, using the unitary transformation that describes the dynamics, and then we take an arbitrary operator on D, then we're requiring that the transformed version of OA commutes with OD, and we're requiring that that happens for all OA and all OD. That's precisely what the condition in white says, and this is an equivalent definition of the idea that A does not influence D to all of the ones that we saw previously. But it's useful when you think about causation in this way, because the algebraic definition makes it pretty easy to see some important properties that quantum influences have. We have time symmetry in the sense that A influences D through the unitary U, if and only if D influences A through the inverse of that unitary. And we also have my favorite property of quantum influences, which is this idea of causal supervenience, sometimes called causal atomicity, which is the idea that influences between composite systems are uniquely fixed by influences between their most elementary subsystems. For example, if A influences D1 tensor D2, if and only if either A influences D1 or A influences D2. This is a kind of remarkable, yeah?
Sorry, maybe I missed it, but what does the U?
U is the unitary transformation. So in this whole setting, we're assuming that A is some input subsystem and D is some output subsystem to some unitary transformation. The unitary transformation is a description of the dynamics. Causation is an idea that's defined with respect to that dynamical transformation.
I see.
So this definition is restricted to unitary transformations, or are you thinking of a Steinspring dialectic? Because previous ones didn't seem to be restricted to that one.
No. They're all restricted to unitaries. Yeah. So I mean, you did see.
Oh, they are used, yeah.
Yeah, there are
The
some.
first one needn't be restricted to unitaries.
So the reason why we're restricting everything to unitaries is related to what I said a second ago about signaling being different to causation. At least if you're taking a sort of if you're taking the view that really every channel is ultimately implemented via Steinspring dilation of some dynamical unitary transformation, then the specific channel that you get from plugging in one of the input states is going to be a kind of reflection of your knowledge in general rather than something that's observer independent. So we define them in terms of unitaries in order to keep the causal relations kind of objective rather than being a sort of agent dependent concept.
So Nick, in the background, you have in mind that the quantum state of the ancilla should be thought of as describing an agent's knowledge, which is why the effective CP map has this sort of epistemic infection, whereas the unitary does not.
Yeah, that's certainly a perspective that fits very naturally with this approach to causal relations. Yeah.
Is it not necessary? Because if somebody said, I think CP maps are the fundamental dynamics of nature, then wouldn't there be some necessity in being able to define causation between input and output for a CP map?
It seems to me that there's also a middle ground, that you can believe that ultimately a full description of the dynamics would always be unitary, but you also believe that the quantum state is ontic. So like Everettians, for example. And I think even on an approach like this, you could reasonably argue for this sort of approach to causation in which you restrict to unitaries.
I see. So as long people can think quantum states are ontic, as long as they agree that there are no, like every CP map does have a dilation into a unitary.
Yeah. I think the more
Causation.
The more important thing is this kind of church of the larger Hilbert space perspective than necessarily the psi epistemic perspective. Although certainly the psi epistemic perspective is going to support this, I would say.
Right.
Yeah. Okay. So yeah, causal supervenience, influences among composite systems fixed by influences among the elementary subsystems. As natural as that sounds, that's really remarkable in the quantum context, right? Because everybody and their dog knows that in quantum theory, states are holistic, states are non-supervenient, right? So if a couple of quantum systems are entangled, then certainly knowing the reduced density matrices of the individual subsystems is not going to tell me exactly what the joint entangled state is. So in some sense, when we're dealing with quantum states, the whole is greater than the sum of the parts. But it's kind of striking that when we look at the quantum theory of causation, really the whole is no greater than the sum of the parts. And one of the ways that that's manifested, something that's implied by this property, is that if I want to represent the whole causal structure of a unitary transformation, then it suffices for me to draw a directed acyclic graph where the only nodes are the most elementary subsystems. Because again, that graph is going to determine, via this property, the causal relations between the combinations of those subsystems.
Where do you get the word supervenience?
It's quite a common word in the philosophical literature. It essentially just, the idea that A supervenes on B just means that B uniquely fixes A. Okay, so that notion and those nice properties allow you to do a bunch of things, which leads to a whole framework for quantum causal models, which generalizes a lot of the stuff that you can do in the classical case. Now, it's not important for us to go through this in any detail whatsoever.
Sorry, could you explain again the last thing you said on the last slide, the supervenience thing? I'm still confused about
Okay, so yeah.
Like, why can't I? So what's the difference between A influencing both? I could think of D1 times D2 as a bigger system. I could have a causal influence on that versus this thing where I see it as a composite system. D1, D2 is the Hilbert spaces, no?
I'm thinking of D1 and D2 as systems. You can think about them represented by Hilbert spaces if you want.
So I could also just say it's not a bipartite system, it's just one thing, and there's a causal inference from A to the whole thing. So I don't understand, if now I see this as a fine-grained two Hilbert spaces, how can I understand this?
Right, so you could just call D1 tensor D2 something else, like E, for
Yes.
example.
And then, if I see it like that, what does causal supervenience mean?
Well, it just means that if there is a way of thinking about E in terms of two subsystems, D1 tensor D2, then causal influence to E implies causal influence to at least one of the subsystems of E, either D1 or D2, and vice versa.
It can be both.
Oh yeah, it can be both.
Okay.
Oh yeah, sorry. This either this or is not an exclusive
Okay,
or. It's
okay,
an
it's not
inclusive or.
exclusive or.
Yeah,
Okay,
yeah.
then everything's fine.
Yeah. Sorry. Yeah. Okay. So good. Quantum causal models. One of the things you can do is extend a lot of the story to situations that suffer from sectorial constraints, which are kind of restrictions on the dynamics based on a decomposition of the Hilbert space of the system into a direct sum of orthogonal subspaces. I won't go into that story really, but I will center a lot of this talk around a concept called an interference influence that can be nicely defined in terms of this framework. So in order to get there, I just want to quickly revise some ideas to do with projectors. So a projective decomposition is a set of projectors on a system that has the property that there's some decomposition of the Hilbert space into a direct sum of orthogonal subspaces, such that each projector projects onto a different one of the subspaces. That's a projective decomposition, and a projective algebra is what you get from taking the span of that thing. So in other words, you can sum together arbitrary projectors from this set, and you can weight the summation with complex coefficients. Okay, that gets you an operator algebra called a projective algebra. With these concepts in mind, we can define a sort of fine graining of the previous notion of quantum influence called an interference influence. We have the same setup as before, this unitary channel. And now I want to say that given a projective algebra PA on A and a projective algebra PD on D, I've got no interference influence from PA to PD, if and only if those projective algebras commute with each other when you transform them into the same Hilbert space. Now, in case that definition is a little bit abstract, perhaps it's helpful to give you a more sort of operational intuition for what this means. We always have to be careful about the relationship between signaling and causation. But if we assume that there's an agent here again and an agent here, and now the agents know everything they need to know about B, then we can sort of conflate causation and signaling. And in that case, we get this operationally equivalent definition of the presence of an interference influence. So there being an interference influence from PA to PD is equivalent to saying that an agent who chooses a channel here that's made out of Krauss operators from PA is able to signal to an agent who chooses a measurement here with operator elements chosen from PD. So on the previous notion, you would allow them to do any channel here and any measurement here, but now it's restricted to these projective algebras. And in case that's still a little bit abstract, there's an even simpler operational notion, which involves talking about this specific measurement on D, which is a projector value measurement that's made out of all of the projectors in the decomposition for D that's associated with this projective algebra. And this notion of an interference influence is saying that the projective measurement you perform up here can sort of be impacted by shifts in the relative phases between the different subspaces that are projected onto by the A projectors. And that's why we call this thing an interference influence. Roughly speaking, and this will be made more precise later on, the sort of intuition here is that the interference influence between the different A subspaces is sort of going to have an impact on which one of the D subspaces gets selected in some way. That's sort of the idea. Okay, good. Now, from its algebraic definition, it shouldn't be too hard to convince yourself that we again get the time symmetry property being satisfied by this conception of an influence. And we also have this causal supervenience property, which is that we get a causal influence from the system A to the system D, if and only if there's at least one interference influence between some associated projective algebras, which tells us that the interference causal structure is strictly a fine graining of the previous sort of causal structure, where what I mean by a fine graining is that if I tell you the structure of, if I tell you all the interference influences, then you can just calculate the causal structure in terms of systems, as it's usually conceived in quantum causal models. And that's kind of nice to know about, because it sort of means that whatever the arguments are for quantum causal structures among systems and quantum causal models being kind of useful, a lot of the appeal of all of that stuff is now going to be inherited by this more fine-grained conception of quantum influence. And most importantly, this kind of quantum influence, this kind of idea of an interference influence, is going to be exactly what we need in order to see how these relational events can emerge naturally from the causal structure.
Just to understand the direction.
Yeah.
The existence of interference influence, is that what you call it? Interference?
Yeah.
Implies the existence of the previous influence. Is that right?
Both ways. Both ways. Yeah.
Both
Yeah.
imply each other.
Yeah.
Okay, so that's okay, good.
Yeah.
That's the error there. Yeah.
Yeah, that's the double error. Yeah. Good. Okay, so we're going to use these interference influences to see events emerging. First, it's important to get clear on what we should mean by an event here. So let's. Oh,
Looks like somebody's trying to speak on the microphone.
Hello. Do you hear me?
hello. Slightly scary. I can't see you, but hi.
Hi, I'm Ila. Can you explain this fine-graining thing again? You said it goes both ways, that if there's a projective causal influence, this interference influence implies there's the causal influence you defined before, and vice versa.
Yeah.
If this is the case, why one is the fine-graining version of the other? It just sounds equivalent.
Okay, so why is it a fine graining? So it's a fine graining because suppose I've got A and D and I'm thinking about all of the different projective algebras that I could have on A and all of the different projective algebras on D. It would take a while, but if you imagine I go through and I check between each pair of projective algebras, is there an interference influence between them? If I go through and check all of them, then if I find that there are no interference influences at all, then that means I can conclude that there's no influence between the systems. But if I do find that there's at least one influence, then I can conclude that there is an influence between the systems. And that's what I mean by a fine graining here. I mean, the sort of list of all of the interference influences contains strictly more information than is contained in a list of all the influences between the systems. Because again, the latter can be deduced from the former. Does that make sense?
But you also said the former can be deduced from the latter. No? You said it goes both ways.
Well, okay. Okay, I see what you mean. So it's important to note this existence quantifier. So if I know that A influences D, then that means I know that there is some PA and some PD between which there's an interference influence. But I do not know which one.
Okay.
Yeah.
I see. Okay, cool.
Cool.
Thanks.
So the more fine-grained causal structure would be a stipulation of all the PAPD such that there is interference influence.
Yeah, exactly. Yeah, and more generally that, but for every input subsystem and every output subsystem to the unitary. Yeah.
And that's what you mean by the interference causal structure. It's a stipulation of a set of choices of these projective algebras on A and D, like all the tuples, PAPD, such that.
Yeah. Yeah, exactly. Yeah, thanks for the questions.
Sorry, so this interference is still no signaling. Can I think of it like steering, like where you kind of affect something on the other side, but there's no way to communicate?
Well, it is connected with signaling. Okay. If you assume that all of the agents have all the relevant kind of knowledge so that we can talk about signaling and causation in the same kind of way, then the presence of an interference influence is equivalent to the possibility of signaling via a particular kind of protocol, which was where Alice chooses Krauss operators from here, and Bob chooses measurement operators from here.
Okay.
Yeah. Okay. Good.
Okay,
Yeah.
So because I'm not following really well. So if I take this projective algebra to be like, your decomposition of the Hilbert space as a dark sum of projective spaces. If I take the dark sum of just one single space, that is the whole Hilbert space.
Yeah.
Okay. In that case, I have your definition on the left, that is this A influence D, no?
No, you'll never get any kind of... so that's a good question. So
PA influence PD is for whatever choice I have of PA and PD, no?
well, it's for a specific
choice. I can choose the decomposition, and I say, okay, for this decomposition, I have this influence between these two sectors, for example.
Yeah.
Okay.
Yeah.
If I take the sectors of A and D to be the whole Hilbert space,
yeah.
So there is no symmetry, no simplification. This is exactly the definition A influence D, or is different?
Is this, what was the last part?
Is it on the left side, on the if and only if, there is A influence D?
Oh, I see what you mean. No, yeah, good. No, it's kind of like exactly the opposite of the case in a way. So if you take your decomposition just to be the whole Hilbert space itself, then your projective decomposition is just going to be the projector onto the whole Hilbert space, which of course is just the identity operator, right? And then your projective algebra is going to be the span of the identity operator, right? Which means that we've just got scalar multiples of the identity. And then remember, the absence of an influence was about the commutation of a couple of operator algebras. This commutes with everything, and so we never get any influence from this kind of thing.
No, I see why you're talking about this.
Yeah, good question.
Another quick question, Nick.
Yeah.
I'm not sure you said it when you were motivating this notion of interference influence, but it's appropriate, I presume, to think of this, like the kind of physical scenario as like a conservation law. So if I cannot modify, which photon number I'm sectoring, but I can modify the relative phases, then that defines the projective algebra where the projectives onto the different number eigenspaces, and that's kind of like a physical motivation for why you'd be restricting to those algebras. Is there a broader set of motivations beyond conservation laws that you have in mind?
So actually, where we're sort of headed towards is something quite different, where we're not just choosing arbitrarily what projective algebras to talk about, but we're also not deriving them from some kind of physical principle like a conservation law. We're rather going to end up with an algorithm for deriving it from the causal structure of an arbitrary unitary circuit. So yeah, it's a slightly different motivation to that, I think.
I'm not quite following that last bit, because it seemed to me that the role of these algebras were something like the scope of possible interventions at a particular point. So I don't see how the causal structure could constrain what somebody at this locus could possibly do. Do you see what I mean?
Yeah, good question. So it might be easier to answer that question towards the end of the talk. For now, I'll just say that when we start with typical quantum theory, and then on top of that theory we build quantum causal models, it might make sense to sort of define our various ideas, our various concepts in terms of the possibilities in principle for signaling between agents who are able to do certain things. I think that the sort of interpretation that we're going to be led to here is going to lead us to quite a different kind of conceptual framework. I hope that the success of that conceptual framework will speak for itself, and I think it's going to lead to a slightly different conception of the origin of these projective algebras. So yeah, we should see later on. Good. All right, so we're going towards deriving events in some sense from these interference influences. First of all, what do I mean by an event? Well, let's say that we've got some arbitrary finite dimensional unitary circuit, and say that given a selection of a few systems like A, B, and C, we want to associate events with all of those systems. I want to propose that we think about events in a way that resembles the approach from consistent histories, where for each of these systems, we're going to imagine that there's some projective decomposition associated with them. And an event is going to be conceived of as the selection of a single projector from a certain decomposition. So speaking very roughly for the time being, and this will be made much more precise, the idea is going to be something like, at least relative to this choice of systems, every time the circuit is implemented, there's going to be a definite fact about which projector from here gets selected, and from here, and from here.
Are those selected at a given time, Or just
If you
each system is I see each Y is a separate system. So does A continues all the way through U1?
no. A is just down here. Yeah. This might be a wire of a different dimension or something.
So that's a different label. Okay, so
yeah.
So that gives you a spatial temporal notion of this.
I mean, not necessarily. You can think about this stuff being embedded in space-time, but you could think of it as background independent too.
Okay, all I'm asking is each wire has a decomposition.
Yeah.
And then that wire stops when you get to U1, and then you have a new wire.
That's right. Yeah, that's right. Okay. Okay, so that's the rough idea. But there should be this burning question in your head, right? Well, you sort of already asked it in a way, which is where do these decompositions come from? Because of course we're dealing with quantum theory, and there's no obvious single choice of which one to use, and we're going to get into a mess if we try to think about all of them at the same time. The answer to this question from the consistent histories literature is that given one specific system, you can choose whatever projective decomposition you like. But when you're thinking about the set of all the decompositions you're choosing for all of the systems, you better make sure that that set of decompositions satisfies a kind of consistency condition that allows you to attribute probabilities to them in a natural way. But as I mentioned earlier, there are good arguments that this is kind of too permissive a way of letting you come up with these sets of projective decompositions. It would be good to have something more restrictive. And as I've already mentioned, our more restrictive answer is going to be that it's going to be derived from the interference influences that are defined in terms of this unitary circuit. So let me give you a sense of why you might expect this to work, just using kind of operational intuitions for now. So we're just going to be using sort of standard operational quantum theory on this slide. We again have Alice with access to the control input and Dexter the target output of a C0. This time it is a quantum C0, so it's the unitary analog of the function that we saw much earlier. Given this setup, it's impossible for Alice to signal to Dexter just by shifting the relative phases between the projectors onto the computational basis. But she can signal to him using any unitary that shifts the relative phases between the projectors in any other projective decomposition. Meaning that there appears to be something special about the 0-1 projective decomposition, at least when we consider it from the point of view of D. And this qualifier at the end, from the point of view of D, is the first sort of hint that it's quite natural to think about events as relational once we derive them from causal structure. Okay, but let's try to actually formulate this rigorously and make it more general by using interference influences. So again, I've still got this setup we've been considering the whole time of a single-shot unitary channel, and A is one of the inputs and D is one of the outputs. I want to say that D prefers the projective algebra PA if and only if three conditions hold. Firstly, I want there to be no interference influence from PA to PD for any PD. Secondly, I want it to be the case that all of the projective algebras on A that are incompatible with PA will exert an interference influence on one projective algebra on D. And then finally, I want PA to be essentially the unique projective algebra that satisfies the first two properties, so that if the above two conditions still hold when we substitute some other PA prime prime for PA, then PA prime prime is just a kind of coarse graining of PA, which essentially means that all the projectors in PA prime prime are a sum of different projectors in PA. Now, I'm claiming that this is well motivated conceptually. I'm claiming that this is kind of the correct definition of preference, but it is a bit of a mouthful. Luckily, though, we can state it much more compactly and more elegantly using some algebraic concepts. So a quick recap of some of those. Suppose I've got a finite dimensional Hilbert space H, and I've got the algebra of linear operators that act on that H, and then I've got some subalgebra X. I want to say that the commutant of X is the set of all of the operators in the big algebra that commute with everything in X, and the center of X is the intersection of X with its own commutant. So in other words, it's the set of all of the operators within X that commute with everything else in X. Turns out that the center is always an algebra, but more than that, it is always a projective algebra, which is a hint that it might be rather useful to us. And it is useful, because according to our previous definition, it turns out to be the case that D prefers PA if and only if PA is this thing. Now that still looks a little bit clunky, but I can easily simplify the notation in an obvious way to write it in a slightly more attractive form. And so what's going on here? Well, if we first look at this bit inside the brackets, then what this bit is is the set of all the operators that act on A, but which also have the property that they commute with all of the D operators. And then I'm asking for the center of that thing. And so this allows us to state the notion of preference more compactly, and it also reassures us that when we apply this notion, we really always do succeed in identifying some PA and a unique PA on A. Good. But we're still not all the way to where we want to be, because so far we only have a definition of preference that applies to single-shot unitary channels. But they're not that great. There's not a lot that you can model with a single-shot unitary channel. It would be better if we could start with some arbitrary unitary circuit like that one and see projective algebras popping up on that circuit. And we can do this if we invoke the definition of a frame, which is just a subset of all of the systems that are involved in that circuit. And now what we're going to do is we're going to give a sense in which projective algebras on the systems in the frame are preferred relative to that frame. The first step is to make breaks in all of the wires that correspond to the frame. And then we're going to put in swap transformations in all of those breaks. Or if you prefer, we're going to sort of pull the outgoing wires to the top and the ingoing wires to the bottom, leaving us with a single-shot unitary channel. And we already know how to define preference in terms of one of these things. We can take the projective algebra on A, which is preferred by the tensor product. Sorry, we can take the we can take the projective algebra preferred on A out, the one that's preferred by the tensor product of all the ingoing systems. And similarly for B out and C out. But of course, all of the important stuff here is time symmetric. And there's no reason to introduce a time asymmetry when we are not required to. So we might as well derive ingoing projective algebras in a similar way. These are going to be the ones that are preferred by the tensor product of all of these outgoing systems. Yeah?
Just one small thing, that if I take PA out, the projective algebra, I would have expected you to say this is preferred by B in cross C in, because your old definition sort of referred to like you would be tracing over A in and then asking relative to B in.
Yeah, I see what you mean.
And then PB out would be defined relative to A in tensor C in. And so
that's a good point. I am like 90% sure they're equivalent, actually. Yeah, because you never get, at least, yeah, you never get any influence in this kind of unitary channel from A out to A in, which is equivalent to the operator algebra for A out commuting with the operator algebra for A in, which means that all of the operators in A just go here anyway. So yeah, so it shouldn't make a difference whether or not we include A in that expression. So I think they're equivalent.
if I remember where it came from.
Yeah, exactly. If you remember that it comes from this unitary circuit.
Yeah, then there's no influence of A out on A.
Yeah.
Okay.
Yeah, that's a good point though. Okay, so we're making progress. Now we've got a sort of algorithm, a function that takes us from a choice of circuit and a choice of frame to a set of preferred projective algebras, where we've got two algebras now for each system in our frame. But we're still not quite all the way there, because what we really want are not projective algebras per se. What we really care about are the events, which, remember, are selections of unique projectors from the decompositions corresponding to the algebras. But we can get there, and indeed it's easy to get there, because we've got this useful theorem that tells us that we can give a natural probability distribution for all of the events in a given frame. So the theorem tells us that the decompositions derived in a single frame form a consistent set of histories, meaning that we consistently can use the probability formula that comes from the consistent histories literature, which I've written here. So this is a frame for n systems. I should mention that in this expression we're using the Heisenberg picture, and that's why we don't see any terms that correspond to the unitary circuit coming up. They've already been absorbed into the definition of the projectors. Now, what does it mean to be able to apply this probability formula consistently? Formally, it means that the probability function is linear. And there are good conceptual reasons for requiring that, some of which are related to the desire to really say that all time evolution is unitary. But leaving that to one side, it's interesting to note in the context of consistent histories that, of course, this function is not manifestly linear, right? Because each of the projectors appear twice. And that's why when you're doing consistent histories, you need to impose by fiat that you've got this consistency condition being satisfied, an example of which is written down here. But the situation is quite different when we derive our decompositions from frames. In fact, we're not going to have to explicitly worry about any consistency condition like this anymore. And this is implied from the following theorem. So that should say when decompositions are derived from a single frame, the consistent histories formula here simplifies to this manifestly linear form. You don't always get the simplification happening in a consistent set of histories, but you always do when your consistent set of histories is derived in this way. And yeah, that function is manifestly linear, and so of course the consistency condition is going to end up satisfied. And it's also interesting to note that this simplification is a direct consequence of the sort of causal structure that inevitably arises from one of these frames. So to clarify what I mean slightly, so after we derive our preferred projective algebras, we can go back to the original unitary circuit that we started with and sort of decorate that unitary circuit with all of our algebras. And then we can, in a fairly obvious way, apply our existing definition of interference influences to determine which pairs of projective algebras influence each other with respect to that circuit. And we find some general facts, like there's no influence between any of the outgoing projective algebras, meaning by time symmetry, there's also no influence between the ingoing ones. We can also show that there's no influence from the outgoing ones to the ingoing ones, meaning that we only get this sort of causal influence. And that's kind of interesting because that means that our causal DAG can always be arranged into two different layers where the causal influences travel from the bottom to the top. And it's this feature of the causal structure that means that we get that manifestly linear form. So it's not too hard to see how this works. We're working in the Heisenberg picture here, which means that the absence of an interference influence just means that the Heisenberg projectors commute. And what this kind of causal structure means is that if we think about an arbitrary ingoing projector here, then we can commute it along the right all the way until we get to the middle. And then we can actually keep on going until it meets its friend, its identical counterpart on the other side of the expression. And then we can take one of them away by the idempotency of projectors. And we can do a similar trick for actually all of the projectors, and we end up with this expression. So to summarize, in consistent histories, it's really you that chooses the preferred decompositions or the preferred projective algebras. And because of that, you have to impose by fiat that this consistency condition holds, even though the general form of the probability formula is not linear. But on this approach, where we derive things from decompositions, we find that the consistency condition has to be satisfied because it's implied by the manifest linearity of our more simple probability expression. And we'll see later a reason why it's kind of useful to require this more restrictive, this less general sort of probability expression than this one. Cool.
Sorry.
Yeah.
Question. So, could you remind me what the definition was of what you call single frame?
Yeah. So we represent the dynamics always with the unitary circuit. That unitary circuit has a bunch of systems. A frame is a subset of those systems.
I see.
And it determines what gaps you make in the wires when you're going to that single-shot unitary channel in order to derive the preferred projective algebras.
Single shot is defined as not simple math, basically.
Yeah, kind of. Yeah, it's just a transformation. It's a channel. Yeah, it's not. I'm more contrasting it with a circuit, I guess, where we're sort of thinking about a channel being decomposed into many different individual channels.
Okay.
So the big criticism of the consistent histories is always that there's multiple sets of consistent histories that seem to tell different stories or incompatible stories.
Yeah.
Are you solving that problem in some sense?
So we certainly are not going for an approach in which there's only kind of one consistent set of histories, or there's only kind of one story to tell about what events happen. Because doing that would seemingly entail responding to the no-go theorems I was mentioning earlier by hanging on to absoluteness, which I think provides a good reason to think you won't be able to hang on to unitarity and relativity theory. I think we have to, on that fundamental point about there just being different consistent histories, I think we got to bite that bullet. But the problems, I don't think that the problems with consistent histories is just the sheer fact that there's more than one of them. I think there are various problems that can lead to, but it's not, those problems are not an inevitable consequence of just the sheer fact of there being more than one.
Okay.
And I'm going to argue that although there's still going to be a multiplicity of consistent histories on this approach, it's a less problematic multiplicity.
Okay, because it solves certain problems.
Yeah.
Like does it address like the Dowd-Kent type?
I believe so. Much more work needs to be done, but I think there's good reasons for optimism on that front. Yeah. Okay, so this leads us towards the promised causal conception of event relativity. I'll just try to explain it very intuitively on this slide, and then we'll see how it leads to a precise theory. So roughly speaking, we're going for the idea now that an event takes place relative to the frame in which the corresponding projective algebra was derived. And what does this relativity mean? Well, one thing that it means is if we get the same projective algebra popping up in two different frames, then we sort of have the same type of event in two different frames, but there's no selection that the events are going to match on every run of the experiment. And also we have another aspect to the relativity, which is just because a projective algebra is derived in one frame doesn't mean it's derived in another frame. And so in one frame we might have a certain type of event, and we just have no corresponding type of event in the other frame. This allows us to make sense of non-absoluteness in an obvious way, because one of our observations now needs to be considered from all and only the frames in which that event emerges from the causal structure. Okay, this leads us to a precise and observer-independent reformulation of quantum theory in an obvious way. So I don't think that this is the be-all and end-all. This is still a work in progress, but hopefully this is progress. First of all, the dynamics are given by unitary circuits, and they're fundamental. The fact that a circuit takes place is taken as a primitive and observer-independent fact about reality. As we know, an event is the selection of a projector. Events take place relative to a frame and correspond to projectors that are preferred in that frame. Events are relational in the sense that if the same projective decomposition features in two different frames, it needn't be the case that the same projector is selected on each run rather. But the fact EF, that an event E took place relative to the frame F, is absolute. We're not doing some kind of relations all the way down thing. An event is relational when you haven't yet relativized it to a frame, but once you do, it's an absolute quantity, just like something like spatial position in relativity theory. And as we saw, we can give probabilities using that linear trace function.
Sorry, could you remind me what the frame was?
Yeah, so you got a unitary circuit, it's got a set of systems, a frame is a subset of the systems.
Okay.
Yeah. So there's a theory, but there's still a question of whether or not it can model all of the right stuff. And I'm going to argue that at least in the finite dimensional case, because again, all of this is finite dimensional, it seems that we can really model all and only the stuff that we want to be able to model. We can do everything that you could do using finite dimensional operational quantum theory. We seem to be able to do all of the stuff like Wigner's friend or extended Wigner's friend, where that typical kind of operational theory breaks down. But we can't do some of the arguably pathological stuff that you can do in consistent histories, but you can't do in the standard approach to quantum theory. So first of all, let's see how we can model a pretty vanilla experiment from operational quantum theory, which could be described as an agent preparing a system of interest in a certain state and then measuring in a potentially different basis. Now that is what I'm claiming is going on in this picture. The first thing you might notice about these pictures, now I've got all these trace symbols. Don't worry about them, don't take them too seriously. Essentially the diagrams are just getting complicated now. I don't want to actually draw the wires going to the top and the bottom of the page, so now I'm just sort of tracing them when I don't want to look at them anymore. You should still think about this as a unitary circuit. I've made breaks in certain wires, and so this picture is really representing a certain choice of frame. And what else? So all of these wires are qubits. The white and black dots are ZX notation for C0 gates. The white dots are always on the control. The black dots are always on the target system. And yeah, okay, so in order to do this prepare-measure experiment, first of all, we take our system of interest and we make it interact via a C0 gate with this qubit, which we can think about as a preparation device. Then you'll see I've got this C0 in the bottom left. The reason why I've put that there is because I know that if I do, then in this frame we're going to get this event popping up that I call Z1. I call that event Z1 because it corresponds to the Z basis. It corresponds to that computational basis projective decomposition. By the symmetry of everything, I'm going to get a similar event popping up here. And once I've done this, it's going to make sense to say things like a state corresponding to the parity of Z1 and Z2. Yeah, the system of interest has been prepared in that state. But that will become more clear in a moment. Up here, this thing is a sort of measurement, because in a similar way to how the parity of Z1 and Z2 corresponds to an initial state of the system, the parity of these guys is going to correspond to a measurement effect later on. Okay, and so how do we get that correspondence? Well, as you know, we can use our linear trace rule in order to get a joint probability distribution for all of these events. We can use that big joint probability distribution to define smaller conditional distributions. And we find that expressions from the usual operational quantum theory pop up in all the right places, such as that one. And it's expressions like these that justify locutions like, I prepared the system in the state Z1 plus Z2. And hopefully you won't have too much difficulty believing me if I tell you that all this stuff can be generalized. These sort of techniques can be generalized in obvious ways. You can go beyond qubits to systems of arbitrary finite dimension. You can do quantum instruments rather than just measurements of a basis, prepare mixed states. You can do multiple measurements, one after the other. You can have multiple labs that are space-like separated. Yeah, you really seem to be able to do everything from the usual sort of theory. But you can do more besides. The usual operational quantum theory would break down. It's not really rigorously applicable when we do something like Wigner's friend, but we can model that here. And this is a scenario in which the relativity of events becomes important, and so we really need to look at least two different frames to get a good sense of what's going on here. So if we look on the left, then we've got a frame in which we've got the systems that correspond to the preparation of the initial state down here, and we've got the friend's measurement over here. And then finally, we've got Wigner's measurement up here, but in this frame, we've not opened up those systems. So somehow this frame doesn't allow you to talk about the perspective from Wigner. And if we're just looking at the bottom part of the frame, oh, sorry, I didn't mention, these two C-naughts form a kind of staircase, and what they are doing is they're kind of undoing this C-naught and this C-naught that are involved in the friend's measurement interaction. Okay, so if we look at this frame below this point, then we see that it's essentially identical to the prepare-measure experiment. So in this frame, we just got a usual prepare-measure thing going on. But in this frame, we opened up Wigner systems, and we find that this point down in the circuit is almost the same as it was over here, with the very important exception that Z4 has disappeared. The projective algebra for the Z basis is no longer preferred in this frame because now it exerts an interference influence over here. Now the preferred algebra for that system is one of these guys. So there's not really any non-trivial event there anymore. And so we kind of recover the common idea that when we consider Wigner's point of view, the point of view of the person who does the measurement on the friend, it somehow no longer makes sense to talk about the friend getting a definite outcome. We're able to make that precise here because we're saying that in this frame, which incorporates Wigner's perspective, we don't have that event popping up at all.
Nick,
yeah.
Can you explain again why the frame incorporates Wigner's perspective?
Yeah, so up here is Wigner. This is, this is a trick we've seen a few times for how you can do a measurement. And yeah, this corresponds to Wigner doing a measurement. And here you can see I've opened up these systems, which allows me to sort of talk about the events that are involved in Wigner's measurement. I also promised to show you that we avoid being able to model the phenomena that we don't want to be able to model. Some of you might have heard about the three-box paradox from consistent histories. It involves this interferometer made out of two hexagonal beam splitters. Really, I think there should actually be a phase shifter over here, but at the very high level that I'm going to describe this, hopefully that won't matter too much. So yeah, in a way that can be made formal using consistent histories, in this paradox what we do is we assume that we know that the particle enters on the left and it exits on the left of this whole apparatus. And we find using consistent histories, this is the bare bones consistent histories formalism, so not where we derive things from projective decompositions, that there exists a consistent set S in which that initial data implies that the particle must have gone down the left side of the interferometer. But there's also another consistent set S prime in which exactly the same initial data implies that it went through the middle. Now, it's only fair to note that this is not a no-go theorem for consistent histories. It is not a logical contradiction. And why not? Because in consistent histories, things happen relative to a consistent set of histories. And these are two different consistent sets. So that's fine. But as Adrian Kent mentioned in his paper where he introduced this phenomenon, it does kind of undercut some of the claims that are commonly thought to motivate consistent histories. So advocates of consistent histories often say that it's Copenhagen done right, that it's just the most natural, modest, and minimal possible generalization of the Copenhagen interpretation. But as Adrian Kent points out, there's really no analog of this in standard textbook or Copenhagen quantum mechanics. There's nothing of the kind where you can infer with certainty both that one projector happens and a different orthogonal projector happens. And so, yeah, arguably it sort of undercuts that kind of motivation. But it's interesting to note from this point of view that we could never model something like this using a consistent history that's derived from a frame. And it's clear that we can't, because if you think about the sort of three projective decompositions that are involved in either the set S or the set S prime, it should be kind of easy to convince yourself that there's going to have to be a chain of interference influences, because these two won't commute and also these two won't commute, because the beam splitter is a bit like a Hadamard gate. And so, arguably, at least, this kind of approach has a better claim to be a sort of the most minimal sort of generalization of Copenhagen that can, alleviate that theory of its usual reliance on concepts like measurement. Good. It's also good to note, just before closing, that not only can we provide ontological models of commonly understood quantum phenomena, we can also classify them. So for example, we find that, we can classify them using the structure of their interference influences, that is. So for example, we find that if we ever want to do a model in which Bell inequality violations happen, then it is necessary that we get a sort of fork of interference influences like this, which opens up a new sort of approach to giving a causal explanation of Bell inequality violations. As is already the case with existing quantum causal models, we've got this idea that there's a quantum common cause of the correlations. But now on this approach with interference influences, it's more precisely an interference common cause, which is it's a less general form of a common cause than, quantum common causes is previously defined. It might be confusing to some of you that now there are these chains of interference influences popping up. You can't have chains within a single frame, but the point of these diagrams is I'm combining the decompositions that arise in the different frames and plotting out the interference influences between all of them. Okay, and it's also interesting to note that there are some interference causal structures which are pretty simple. I mean, this one is just as simple as this one, for example.
Wait, can you go back and say that again? Like, it's impossible to consider a chain in a single frame?
Yeah. So if I just restrict myself to the 2n projective algebras that are derived in a frame of n systems, then they will never form a chain of interference influences. But if I've got one unitary circuit and I consider two different frames, and I combine all of those projective algebras together in the same circuit, then I might find that there are chains. And I will have to find that there are chains if the circuit is going to represent a Wigner's friend type phenomenon. We've got structures like this that don't correspond to any often talked about quantum phenomena or no-go theorems that I'm aware of, at least. And assuming that's not just my ignorance, then that's kind of cool, because maybe by exploring these pretty simple interference causal structures, we might be able to find something new and interesting. Okay, so now just some concluding thoughts, I guess. So I started by talking about these two key developments in quantum foundations, the first one being these no-go theorems for the absoluteness of observed events. I pointed out that there are very good reasons to reject absoluteness, and yet it's very hard to come up with a satisfactory understanding of why and how events can fail to be absolute. Often you get problems with things like theory confirmation, like the Everettian branches that don't follow the Born rule, or consistent histories difficulties with explaining the persistent, approximately classical character of our experiences. And then you had relational approaches which didn't seem to suffer the same problems, but were a bit too vague. I hope that with this kind of theory, we've been able to improve on those issues quite a bit. Certainly we don't get the Everettian nightmare of non-Born rule frequencies. All of the frames are going to follow the Born rule. Something that I've not had too much time to talk about is this issue of persistent quasi-classicality. A lot more work needs to be done on this, and a really satisfactory analysis would involve extending all of this stuff to the infinite dimensional case, which is really one of the next most immediate items on the agenda. But I think it's fair to say that there are good reasons to expect that we are going to improve on that front. So the thing that you want when it comes to explaining persistent approximate classicality is you want to be able to focus on the consistent histories that are made up of these projective decompositions with projectors that sort of project onto objects being approximately localized in position and momentum and so on. And then you want them to follow approximately quasi-classical trajectories. I think there are good reasons to think that when we derive the decompositions from the causal structure relative to a frame in the way that we have, that these are the kind of projectors that we expect to see coming up. We formalized some of the ideas from relationalism, certainly the idea that events emerge from interactions. We've almost formalized the idea that events are relative to a system, but not quite, because in relational quantum mechanics, typically you're thinking about this localized system, and here, by contrast, the sort of globalism is really important. A frame with one system never includes any events at all, so it wouldn't work if you just considered a single localized system. And yeah, okay, so maybe I'll just conclude with a couple of issues with this theory as it's currently stated and ways that it might be improved upon. There is this very nice paper that's quite recent by Emily Adlam about the role of intersubjectivity in physics, and quantum physics in particular, in which she criticizes some of these perspectival or relational approaches to quantum theory on the basis that they involve this kind of what's sometimes called a sort of island ontology or island universe ontology, in which you've just got the perspective of these different localized systems, and one perspective never tells you anything else about a different perspective. It's not hard to see how this can create problems for science and the confirmation of scientific theories. I don't know about you guys, but I've not personally done much in the way of actual quantum experiments. I'm a theoretical person, and so the only reason I have to believe that quantum theory is true is the testimony of other people. But if my perspective has nothing to do with the perspective of those people who I perceive are telling me something about what their experiments are, then it seems like I might not be able to trust their testimony. Now, I also think that when we keep with this axiom, our theory is vulnerable to this kind of objection, because we do have some kind of silly frames that are very small and arguably only include the perspective of one observer, say. So I think we could be led to a similar kind of problem, but luckily I believe that there is a natural fix which is basically replacing the frames with frames that are in some sense maximal. You can ask me more if you like about precisely what the definition should be, but the idea is that if one frame allows you to talk about strictly more events than another frame, then the first frame is not maximal. Yeah, so I won't say anything more about that. And finally, I'd like to make a point about dynamics. So as you'll probably remember, throughout, I've been talking about starting with a unitary circuit, which is the whole dynamical structure. But I said that causation was a coarse graining of dynamics. And also, the only important thing when it came to deriving the projective algebras was the causal structure. And so you might reasonably ask whether we can sort of get rid of dynamics and just talk about the abstract causal structure. There's a relevant technical question there, which is given two unitary circuits with the exact same interference causal structure, do they both always lead to the same probability distribution for the projective algebras that I described? If they do, then it seems pretty clear to me that we can replace this first axiom with an axiom about causation. And that might be a kind of interesting thing to do. There's a paper by Rob, in fact, which argues that we should be trying to overcome this kind of traditional dichotomy between kinematics and dynamics on the basis that the boundary between those two things is kind of conventional, leading to the suspicion that it's not really a particularly fundamental distinction. And the argument in that paper was that we should replace it with something that doesn't have such a shiftable boundary, and that thing might be causal structure. If we are able to replace this axiom about dynamics with an axiom about causal structure, then not only will this theory allow us to get over thinking about the idea of a state or even the idea of an event as being a kind of fundamental entity in physics, and there being this distinct thing called the laws of nature or the dynamics, which give you the rules for how those first things evolve. If we are able to replace this assumption with something about causal structure, then we'll overcome this states versus dynamics dichotomy, and we'll be able to really think about physics in a somewhat more unified way, I think, in which we've just got this primitive concept, which is the causal structure. And then our ontology are just events which are algorithmically determined from that causal structure. So I think that's the next thing to look at. And I will stop there. Thanks.
All right. Thank you, Nick, for the extraordinary talk. I haven't heard such a new formulation of quantum theory for a long time, apart from some crackpot ones. But this was extraordinary. So thanks a lot. So we're getting close to the end, but I think we have time for a couple of short questions. So, Rob, go first.
I have a few. So first, just a clarification. Didn't quite understand when you said we could achieve observer independence, perhaps by switching from frames to maximal frames. Wasn't clear what the definition of maximal frames were, but in particular the Wigner-Friend example, where you have the friend and Wigner, it seemed to me that if you tried to include a frame that had both Wigner and his friend, probably you'd get trivial stuff like. So what's the state?
Oh yeah.
Friend can show you that intersubjective agreement clearly is not going to be achievable simultaneously with any sort of interesting events happening.
No. That's an important clarification. So it's not that I expect or even want to be able to recover intersubjective agreement in these exotic Wigner's friend type scenarios, but I do at least want to avoid them in non-exotic scenarios in which decoherence is taking place and so on and so on. And I'm saying that in order to achieve intersubjective agreement, or in order to secure it rather, in those non-exotic scenarios, I think we need to switch to defining our ontology in terms of only the maximal frames.
And the maximal frames would be like, oh, let's throw in all the observers we can, roughly speaking.
Yeah, something like that. I mean, you have to bear in mind that the word observer is not part of the fundamental language of this theory, but you'd want to define a notion that somehow recovers that idea. Yeah.
In that sense, there would not exist a maximal frame that includes both Wigner and friend.
Exactly. Yeah, there can't with the Wigner's friend thing, because as we saw when we included Wigner, that event for the friend disappeared, so we can't really talk about the measurement outcome in this frame. So exactly, there won't be a maximal frame that includes both Wigner and the friend's experience. Although also there won't be a non-maximal one either. There just isn't a frame where that happens.
There will be one. It'll just have trivial dynamics, right? Everything will be a diagonalizable on the same basis. You won't have any valid equality violation. But there is a frame in which you cut everywhere.
Yeah. So this is a frame. This is a frame, and there's nothing wrong with this frame, right? The set of all the systems where I've made breaks. But in this frame, which does include both the friend and Wigner, we don't have the sort of event that we would need in order to talk about the friend obtaining an outcome. So yeah, there exists a frame, but it's just not describing everybody's experiences.
Wait, maybe Lucian had a question.
So just clarifying the questions. If you choose a frame, then there exists a unique. So it wasn't one of a set of events. Is that the unique?
Yeah.
Okay. But it may be trivial.
Yeah.
Okay.
Yeah.
So then the consistent histories approach, it's a while since I studied it, you have something like the three-box example,
Yeah.
it gives you non-trivial ways of thinking about that. Whereas, although it has this contradiction, whereas this apparent contradiction, whereas in that case you only have a trivial, you don't have a way of thinking about the three-box example. Is that you can choose non-trivial?
Yeah, I guess the point is that yeah, you would never be able to model it in such a way where you opened up all of the relevant frames and you got non-trivial events. Although actually, I don't know if that's the right way to put the point, because we have to bear in mind that, yeah, the most fundamental difference with our approach in consistent histories is that you're deriving the preferred projective algebras from causal structure. And so if you just wrote a circuit that corresponds to the three-box paradox scenario with the interferometry, then there would be a more trivial reason why we don't get this paradox relative to that circuit, because that circuit just doesn't have the right causal structure in order for you to talk about the events that you need to talk about in order, or the decompositions you need to talk about in order to formulate the paradox. But then you might think, okay, maybe I can be kind of inventive, and maybe I can write down a different circuit, and maybe somehow that will give me qualitatively the same phenomenon. But that's where the argument that I made earlier comes in, which says, no, there's just a sort of no-go theorem, if you like, that tells you can never have a three-box paradox in our theory. And the reason for that is that you would need to have a chain of interference influences within one frame, but you never have that.
So you still want to be sure that you got enough structure to talk about the world meaningfully. So if you're ruled out from talking about events in certain situations, because here's a theory where I can always calculate the unique set of events, and that is just a trivial set of events. So there's my theory.
Yeah.
That's not very good, because
absolutely.
it doesn't say very much about the world. So we want to be a long way from that.
Yeah.
So you want to be able to, in any given situation, talk about something that's meaningful, presumably?
Yeah. So the claim that I'm making is that anything that you can model using your Nielsen and Schwang type quantum theory can be given an ontological model using our interpretation.
And you can make meaningful statements about that way, because it won't always be trivial. There'll be some.
Sorry, say again.
It won't always be trivial. Like there'll be some non-trivial stuff you can say.
Yeah. I mean, this stuff is an example, right, where we've got a scenario that can be described using your textbooks using expressions like this. But we can write down a frame in which we get these events emerging, and we sort of recover those expressions in the places where we would expect.
Then one other question, because it emerges from the causal structure, you can have a circuit that goes on for a very long time, like millions of years into the future.
Yeah.
So does the sort of stuff I'm allowed to talk about today, it would depend on potentially on a frame that goes on into the indefinite.
Yes.
And my conception of reality at the moment depends.
Yes, this is. Yeah, so this might be unattractive to some, but this is a highly global interpretation of quantum theory. It's true.
Has a sudden block world sort of built to it in some sense.
Yeah, it definitely fits naturally with that block world kind of intuition. So personally, this is not a theory that this is not a feature of a theory that I could choose if I could choose everything that I wanted in a theory without getting a contradiction. I think it's much nicer in general when you do have a theory where you can think of everything being atomic, everything being built out of little pieces. But it's also my opinion that if you want to respond to the Wigner's friend paradox and the Wigner's friend no-go theorems in a satisfactory way in which you hang on to unitarity and relativity theory, I don't see a way of doing it that avoids this some kind of global feature like this. You got something kind of similar in Everett, for example.
Anyone else have any questions? I have another question.
I just wanted to ask, can you specialize this to recover classical causality? Right, so classical causality, we have typically, we can talk about, we know what the dynamics are, we know how to find functional dependence. It's not usually defined in terms of unitaries.
Yeah.
Most of that's irreversible processes.
Yeah.
So I would think even if you impose everything commutes with everything.
Yeah.
Everything's sort of diagonalizable on a single basis. And you apply this definition and say, what do you get? Well, then certainly events can occur, you can have the maximum effect is everything. But can you really recover classical causality where you need to define causality for irreversible processes?
I hope so, and I'm thinking probably we can. We have sort of just very recently started thinking about that. But yeah, I don't really have any. I guess I don't have much in the way of concrete details on that. But we should absolutely discuss that more later if you're interested.
Right. Go for another question. So I'm curious what philosophical camp you land in with this sort of approach. Some of the things you said kind of are suggestive that you're going for a realist interpretation. You referred to it as an ontological model at one point, kind of emphasize observer independence.
Yeah.
But when I think about like the story that emerges for Bigner's friend, which is kind of similar to the feature of consistent histories, that the story you tell depends on kind of the question you ask, the frame you set. That when I read the consistent historians,
Yeah.
Even if they may not be quite the same as Copenhagen, there is a kind of instrumental bent. They want to say something like, asking for some sort of God's eye view of what's going on and a single story, that's too much. Really, what we want is more kind of instrumental. We want to say, if you've got a question about what's going on, here's a story that'll be appropriate for that question. And if you've got some other question, then here's a story that'll be appropriate for that. And I see that as kind of like a very strong empiricism or instrumentalism in consistent histories.
Yeah.
And it feels to me like you've got to give up, I think, on some of the objectives of the realists if you want to maintain this relationalism of what sorts of events obtain.
Yeah. So I absolutely am of the kind of realist philosophical bent, and I think that at least if you're happy to say that the kind of relativity that we get in relativity theory is not in contrast to realism, then I think we can say the same thing here. So in relativity theory, right, if I've got if I've got an object A over here and an object B over here, then we can ask what's the spatial interval between them, right? What's delta x? But that's not absolute in relativity theory. It was in pre-relativistic physics, but no longer in relativity theory. That's not absolute. But delta x relative to f, where f is a reference frame from relativity theory, that is absolute. It's an absolute fact that when I use this particular frame, I get this particular kind of distance between them. And so you can still talk about absolutes. There are still absolutes in relativity theory. They are just not the thing that you initially expected they would be, right? It's different quantities that are absolute compared to what you thought. Now, similarly, on our approach, you could say, okay, what event happened at the system A? Or, okay, let me just write it as an E. And that thing is not absolute. But once I relativize it to one of these frames in our sense, that thing is an absolute quantity. So you never have to use locutions like, although, yeah, it's possible that I slipped into that from time to time. You never have to use locutions like, we can tell this story when we think about this frame, or we can tell that story when we think about that frame. It's just a fact that E happens relative to F. That's absolute. And it's a fact that E prime happens relative to F prime. So yeah, I don't think there's anything essentially instrumental or empiricist about this.
Can I push back gently on this? I think there's a contrast with relativity, because in relativity theory, let me use a slightly different example. Say I have a meter stick. The length of that meter stick is frame dependent. Alice says it's one length, Bob says it's another length, because they have different notions of simultaneity. But relativity theory provides me with a picture that can sort of unify all those different points of view. I can say, look, there's the world tube of this meter stick, and what Alice calls its length is one slice of that world tube, and what Bob calls its length is another slice. So they're just two properties of this one thing, which is the world tube. Once I've told you the world tube of the meter stick, I've told you everything. I don't need to frame that description as, it's this relative to this frame, that relative to that frame. I can deduce all that. All those facts can supervene on the one world tube description.
Yeah.
As long as you're lacking, though, that deeper description on which everything supervenes, that it feels to me that you don't have the kind of realism that we have in relativity. You have something weaker that feels more instrumental.
So I don't know if the distinction is so... certainly I agree that there's a distinction, and it's kind of more attractive how in relativity theory we can just kind of change our concepts and we can get a more compact description than we would get just by listing all of the quantities like this. But kind of trivially, we can at least get a description in this kind of quantum theory that describes everything that happens, right? We can just list all of the events that happen relative to all of the frames, right? As in, for every frame, we can list all of the events that happen. So there is a single and unified description of everything that happens in the world from which all the frame-dependent descriptions can be deduced. I guess that the difference with relativity theory is that currently we don't have any like compression algorithm for that unified description. We don't have a way of condensing it. And it's definitely, yeah, I mean, it's definitely an interesting question to ask whether or not it is possible to kind of compress this information in any way. My feeling about this is a pessimistic one. It seems to me that, well, yeah, the expectation that I have from extended Wigner's friend and all of those no-go theorems is that you won't be able to get this kind of compression algorithm. But maybe I'm wrong, and I would love to be wrong.
All right, we have 2 minutes if anyone else has any questions. PhD students are also allowed to ask questions. So,
Encouraged.
encouraged, yeah. So, okay, well, if not, then I think we should thank Nick again.
Thanks.